Okay, so here we have 11.1 electromagnetic induction, paper 2 questions. So we begin at the beginning. We have a circuit involving capacitors. We haven't done capacitors yet. They are part of topic 11, but there is a part where I believe there's an EMF portion of this. Let's take a look. Okay, I found it. So yeah, we have these capacitors and they're connected. You can have capacitor A or capacitor B, and then there's a question there's a portion talking about two nested coils. That's actually called a transformer. We'll be talking about that soon as well. But here's this graph of magnetic flux against time. It's talking about the induced magnetic flux in the secondary coil, that's coil Y, that's not connected to the power supply. But because of the nested coils and Faraday's law and Lenz's law, there is a current and magnetic field induced in coil Y, and that magnetic field against time looks like this graph. And based on this graph, we can figure out the EMF in the secondary coil in the first 3 milliseconds. So I'm going to cross out the ones that we don't need. It's 3 capacitor questions and a transformer question, but we can do 1E, and we don't need any additional information to do it. And at first blush, I thought we would need to do something involving the slope of a tangent line to this curve, but it's actually asking for the average EMF across all 3 milliseconds. So we're just going to need the change in the magnetic field over the change in time, but we still also need the number of coils and we need the area. And so I said we don't need any additional information. That was wrong. So let's see, how many coils are there in our loop? This is second coil of cross-sectional area 6.4 centimeters squared. So let's write that down. And I believe it said that there were 5 turns in the coil. Yes, 5 turns in the coil. So we know the area and we know N. Also, the way the coils are nested, the magnetic field from coil X and the area vector of the coils Y are parallel to each other, so that cosine of theta is going to be equal to 1. We just want to convert that 6.4 centimeters squared to 6.4 meters squared. And there we go. So 6.4 centimeters squared is actually 6.4 times 10 to the negative 4 meters squared. And then the change in the magnetic field, we go from 0 to 7.5 in 3 milliseconds. Of course, be careful, the magnetic field is in millitesla. So I have 7.5 times 10 to the negative 3 Tesla. And my time is 3 times 10 to the negative 3 seconds. And I work it all out. I get negative 8 times 10 to the negative 3 volts. And it doesn't actually say, I think it's just looking for the amount. I'm not sure if the negative actually matters. And the 3 points are for the equation, for the worked math, and for your final answer. Okay, number 2, we have a magnet that's falling through a coil. That is definitely an 11.1 question. Okay, so 2A says, write down maximum magnitude of the rate of change of flux linked with the coil. And so you might think that the rate of change of flux, it's looking for the maximum value of the slope of this graph. Not the case. Notice that this graph is EMF. This is a graph of EMF. EMF is the rate of change of flux. Let's remember that EMF is negative the time rate of change of flux. So when 2A says write down the maximum magnitude of the rate of change of flux, it's really saying, based on the graph, write down the maximum value of the graph. And it says magnitude, so positive and negative do not matter. And so the EMF ranges from 0 in the beginning, goes up to positive 3 millivolts, goes down to negative 5 millivolts, and then returns down to 0. And so the maximum magnitude, the biggest number, is right down here. And so that would be 5 millivolts. You can say 5 times 10 to the negative 3 volts. But yeah, it's pretty much just saying the maximum magnitude of the rate of change of flux linkage, which of course is the EMF itself. So, and it's only 1 mark, so it's actually a pretty easy question if you realize what they're asking for. And then 2b says, write down the SI unit, fundamental SI units for your answer to A. I don't know why it says AI, it's not I, it's just A. But fundamental units for a volt. I don't know if this question is necessarily an 11.1 question, but I mean, fundamental units are applicable in every unit. So voltage V equals W over Q, but Q in coulombs. Coulomb is not a fundamental unit. Ampere is. So the 2 formulas I'm going to reference are V is W over Q and I equals Q over T. And so a coulomb is an ampere second. Now, work, of course, is measured in joules, but joules are not fundamental. So yeah, a volt is a joule per coulomb, a coulomb is an ampere second, and a joule is a kilogram meter squared per second squared. So we can just reduce this, simplify, that's the word I was looking for. And so in the end, we combine the s to the negative 2 with the s to the negative 1, and we get that a volt is a kilogram meter squared per ampere seconds cubed. So those are the fundamental units. All right, now to see, why does the graph become negative? I don't know that we, so for 2c, explain why the graph becomes negative. I don't know that we necessarily need to say why the EMF is positive to begin with. I think it's because, again, EMF is the first derivative with respect to time of flux, and flux is NBA cosine theta, and so the derivative of cosine is negative sine, but EMF is negative the derivative, first derivative with respect to time of flux. So negative of a negative is a positive, and so I think that's why the EMF starts as positive. That's not what they're asking, though. They're saying, why does it become negative? Why does it start positive and become negative? And that's because the induced magnetic field switches poles, and here's why that's true. All right, so bar magnet approaches the ring, the flux in the air is increasing, so the EMF in the coil makes a magnetic field to oppose it increasing flux. That would be Lenz's law. Then as the magnet passes through the middle of the coil, there really is no net change in flux. So since there's no net change in flux at that instant, there's no EMF. So the EMF at that instant in time is 0. So that explains why we have an increasing flux, and then all of a sudden the flux drops to 0 in the middle. That right there, that EMF in the middle, boop, the magnet in the middle of the coil. And then it falls through the coil. But now as it's falling, that magnet is now moving away. It's now receding. The magnetic flux is getting weaker. And so the EMF, instead of seeking to oppose an increasing flux, is now seeking to reinforce a decreasing flux. And so then in that case, the EMF, the magnetic field will need to switch directions at that point. And if you're going to switch the magnetic field direction, then the EMF will switch sign from positive to negative to send the magnetic field in the coil, the induced magnetic field, in the other direction. And so that's why the graph becomes negative. Okay, so 2D is making reference to the area under the curve of the graph. So let's go take a look at that graph again. Here it is. And so the area under the curve is always the y-axis times the x-axis. So yeah, the area under the curve would be the EMF times the time. So let's remember what EMF is. EMF is negative the change in flux over the time. And so the area would be the EMF times the time. EMF is negative the change in flux per unit time. And so the time actually cancels. And so the area of this graph is the total change in flux. That's important to realize. All right, so realizing that, It says, why would the areas above the time axis and below the time axis be the same? And those two areas are the same because the total flux that's coming in, the magnet kind of coming, the inbound magnet, I guess you could say, that flux going in, has to equal the total flux coming out. Magnet is inbound with its flux and then it leaves. So it brings the flux in and then it takes the flux with it. It's not like something that gets left behind. So yeah, the total flux coming in equals the total flux coming out, and so the areas are the same. Does it say why the shapes are different? No. I will just comment on that. It says, we can see that the flux for the beginning was more. The highest in the first peak has an induced EMF of 3 millivolts, but the peak going down has an induced EMF of 5 millivolts, and you might figure out that's because the magnet is falling, and since it's falling, this is released from rest, it is going slower above the ring than below the ring where it's going faster since it's accelerating, and the speed does matter. The speed affects the rate of change of flux. So the faster the magnet goes, the higher the peak is going to be on the EMF graph. And so that's why the first peak is shorter than the second peak, because in the first peak it is moving slower than in the second peak. And that actually does play a role in 2E when it says, what if the magnet were dropped from a lower height above the coil? So if the magnet were closer to the coil, what would that do? How would that affect the graph? Okay. I really love the paper 2 questions much more than the paper 1 questions. I think they just kind of make more sense. But anyway, so this guy says, what would happen if you drop the magnet from a lower height above the coil? If you're closer to the coil, then it's going to be slower as it passes through the coil. And like I just said, that the speed of the magnet affects the rate of change of flux. And if you have a lower speed, you have a lower rate of change of flux, and so there's less EMF that's created. If you have less EMF that's created, then the peaks of the graph are going to be shorter because you're getting less EMF. But since it's slower, it's going to be spread out over greater time. So the peaks will be shorter, but the bases of the peaks will be wider. They'll be more spread out. This also allows for the fact that the area of the graph is going to be the same. So the peaks are going to be shorter but wider, thereby giving the same area. Has to be the same area because the area represents the total change in flux. That's what we said over here. And it's the same total change in flux whether your magnet is fast or slow. So there you go. And that's the end of number 2. And here we have number 3, and we have a loop that's passing through a magnetic field. Okay, so the loop is entering the magnetic field, and it says that the field is 65 centimeters from end to end. We know that the loop is square, so each side, it gives one side is 5 centimeters, and so each side of that loop is 5 centimeters. We know the magnetic field strength is 0.94 Tesla, and that's about it. It takes 3.5 seconds to move across the field, and it says the speed of that loop is constant. So show that the speed is 20 centimeters per second. That really shouldn't be that bad. We know that average or constant speed is displacement over time, and so the displacement is 65 centimeters plus an additional 5 centimeters. So if we go from the leading edge moving across, the leading edge moves across the field, that's 65 centimeters, but then this same leading edge, it's the back side exits the field, so the leading edge had to go an additional 5 centimeters, so that displacement is 65 centimeters plus an additional 5 centimeters over a time of 3.5 seconds. And so that gives us, that's 70 divided by 3.5, and that gets us 20 meters per second. All right, next question. Sorry, that's 20 centimeters per second squared, not 20 meters per second squared. All right, we have a graph of magnetic flux linkage against time. So since the loop is moving, then there is a change in flux happening. The loop is moving through the field, so there is a change in flux. So there will be a flux linkage, or in other words, an induced magnetic field in the loop. And so we know that the loop is moving at 20 centimeters per second, and the loop itself is 5 centimeters on a side. So as the loop enters the field, we start being outside the field with 0 flux, and then as the loop enters the field, it eventually it is entirely in the field once the 5 centimeters has crossed into the field. And at 20 centimeters per second, a 5 centimeter loop is going to take a 0.25 seconds. It takes a quarter second in order for the loop to fully enter the field. So from 0 up to 0.25, we're going to have a steady increase in the field, in the induced field in the loop, and then the loop moves steadily at a constant speed across the field. But then, just as it takes a quarter second to enter the field, it takes a quarter second to exit the field. So from 3.25 to 3.5 seconds, we're going to have a decrease as the loop exits the field. But otherwise, it's a constant flux as it moves across at constant speed. Kind of draw a little thingy right there for that. And it just says sketch the graph. It doesn't actually ask for anything on the vertical axis in terms of a value. And all right, so that's 3b is what the flux is doing against time. 3c is what is the EMF doing against time. EMF, of course, is the change in flux per unit time. And so that's pretty much, that would be the slope. Let's see, EMF is the slope of the phi versus t, flux versus time graph. And I guess this is just, it says the magnitude, so we just want the amount of it. The sign doesn't actually matter. And so we only have a slope in the first quarter second and the last quarter second. And so this EMF, we're going to have an EMF value in the first quarter second, and we're going to have an EMF, the same EMF value in the last quarter second. Otherwise, we have no EMF. All right, so yeah, we have EMF is the negative, the change in flux over time. I know that flux is NBA cosine theta. We know the number of turns. We know the magnetic field strength. We can get the area from doing side squared because it's a square. So that's 25 times 10 to the negative 4 meters squared. And then the maximum EMF, we only get an EMF in a quarter second, in the first quarter second and the last quarter second. So it's the same amount of EMF. So just pick 0.25 seconds for your time. And so what you wind up with is 0.8 volts for your EMF. So there's 3D. Okay, so 3E gives the resistance, and what's the force on the loop as it enters. So as it enters, there would just be one side of the loop. So we can do F equals BIL, treating just the length of one side as kind of like a wire. And then the velocity of that wire, the incoming wire, is to the right, which is at right angles to the field. So sine theta winds up being 1, so we just have F is BIL. Now we have a number of turns in the loop, and so each turn experiences the force, and the more turns there are, it's a multiplier. So we have force is the number of turns times BIL. So you have 85 turns. Magnetic field strength is 0.94 Tesla. The current is 0.33 amps. I did that with a little R equals V over I, or I equals V over R, using the voltage from 3D, of course, to get 0.33 amps as the current. And then the length of that one side as it just enters the field is 0.05 meters. because it's 5 centimeters. And so we throw all of that together, multiply it up, and we get 1.3 newtons for our force. And then 3F and 3G deal with energy and temperature, and we're not going to worry about that right now. I just want to focus on the 11.1 stuff. So that's the end of 3. All right, we still have some more to do. Now let's keep going. So we have number 4, and we have a coil that is rotating in a magnetic field that is going into the page, and it wants to know how is an EMF induced in the coil for 4A. Okay, so 4A wants to know, why is there an EMF induced in the coil? So let's take a look at EMF. So, sorry, EMF is negative, the change in flux per unit time, and flux is NBA cosine theta. So as this coil turns, it doesn't change the number of coils, the N count. The magnetic field is constant and the area of the coil is constant, but so yeah, by rotating the coil, it changes the angle between the area vector and the magnetic field direction. That change in angle gives the change in flux that would induce the EMF. And there you go. Note that in my solutions, I use symbols like flux and theta. If you write symbols, you should, especially if it's a explain question, you should maybe write out what those symbols are, just so that you have an awareness of, like if you write down phi or theta, you actually know what those symbols really are, what they represent. So yeah, that's 4A. Here's 4B, let's give it a look. Okay, so for 4B, we have this graph of voltage versus time. And it says once 4B, once the root mean square, I do believe that's 11.2. That's a valid and very close question, but it's not 11.1. And then is talking about stepping up stepping up or stepping down or whatever, that is a transformer. That is not 11.1. It's soon, but not yet. Then 4D says you double the frequency with no other changes being made. Draw on the axes the variation with time of the voltage output of the generator. Well, if you double the frequency, then you will halve the period. So the time for one cycle will be halved. So going up to this graph, the cycle here completes in 20 milliseconds. It will now complete in 10 milliseconds. But the voltage changes as well, because we know from Faraday's law that the EMF is negative the change in flux per unit time. And so if the delta t, if I can increase the frequency and decrease the period, if the delta t goes down, then the EMF is going to increase. And so if I do the same change in flux in half the time, that is going to double my effective EMF. So this cycle is going to complete in 10 seconds, but it is also going to have, it's also going to double the amplitude from 25 kilovolts to 50 kilovolts. And the mark scheme says you'll only have to draw one cycle. So there's my one cycle. And again, just to be clear, we're looking at 4D here. Number 4D. All right, and then 4 is over. So now we're into 5. And then 5A seems like a confusingly obvious question, but it doesn't say why is the flux increasing as the magnet comes towards the ring. It says why is the flux from the ring increasing? And that's because of Lenz's law. All right, and then it says while magnet moving towards the ring, sketch the direction of the induced current in the ring. So we have an inbound north pole of the magnet. So the induced current is going to make a magnetic field to oppose that. So then the induced magnetic field will point upwards to oppose the incoming north pole. So viewed from above, that would give us a counterclockwise direction. And it's counterclockwise using conventional current because of the right-hand rule for loops. Again, the thumb pointing straight up would be the direction of the magnetic field, and the curled fingers would be the direction of the current. I don't really get the point of 5C, because if you can answer 5B, then you understand Lenz's law and why the induced magnetic field is approaching the incoming magnetic field. But it says deduce the direction of the magnetic force on the magnet. But yeah, if you can answer 5B, then you can answer 5C. I guess they just want the explanation behind 5B. 5B is just draw some arrows. 5C is kind of explain what's going on. But yeah, Lenz's law will make a current in the loop to make a magnetic field to oppose the change in flux, the increasing flux. There's an incoming north pole, so the induced magnetic field makes the north pole to oppose it. That force on the magnet is opposing its motion. And then with number 6, you may remember this question from such hits as topic 10. But we already answered a bunch of these, so show the orbital speed is 8 kilometers per second. We already did that. And then it says why are the orbital times for x and y different? Why does satellite Y require a propulsion system? We don't need that. But here we have, we look at that. We have a magnetic field. And so satellite X and Y are connected by means of a tether. And so we have a conducting cable moving in a magnetic field. And so why does satellite X become positively charged? Because of induction. Now, it says explain why. This is 3 marks. So you can't just say because induction, duh. You have to be a little more specific than that. If you're wondering if the cable that connects X and Y is in fact electrically conducting, it does in fact say that in the problem. So you can't be like, we don't even know if it's a conductor. Yes, it is a conductor. So we have a conductor moving in this magnetic field. My foreshortened right hand is really just not happening, but I will kind of like redraw this with an upward magnetic field at the point where the satellite is. The velocity of the system is into the page, so I'm going to represent that with circle X, velocity, and then this is magnetic field. And so with the velocity going into the page, and that would be the thumb, so the thumb of the right hand, thumb of right hand, and then the magnetic field are the fingers of the right hand. Then the force coming out of the palm would be moving the force on the positive charges would be towards the right, and so that would put a net positive charge on Y and on X and a net negative charge on Y. I'm honestly not quite sure what they're looking for in 6E. It says, why is the current going to become 0 unless there's a method for transferring charge from X to Y? I mean, the current in the cable is going to be 0. I mean, basically, the current is not going to happen unless you have a closed path for the current to flow through. I'm even reading the mark scheme here. It says, electrons will build up at satellite Y and a positive charge at X, preventing further charge flow by electrostatic repulsion. I don't know what they mean by that. And is it unless a complete circuit exists? I feel like that's kind of saying the same thing. I don't really know where they're getting 3 marks from. The mark scheme it doesn't actually indicate where the 3 marks are coming from. So yeah, I don't know. Let's move on. Incidentally, my quibble with this question is not the answer. The answer is pretty much there's no closed loop, and you need a closed loop for current to flow. I really don't know where they're getting 3 marks from. But whatever. Let's complete. This is the last question, so let's finish it. So 6F actually uses an equation that we talked about at the very beginning of 11.1 and haven't come back to, and that's that the EMF in a wire moving in a magnetic field is the magnetic field strength times the velocity of the wire times the length of the wire. And so we get 31 micro Tesla times 8,000 meters per second times 15 times 10 to the 3 meters. The speed is given. If you're like, well, what's the speed of the satellite? It's actually described right in 6A. Show that orbital speed is about 8 kilometers per second. That's where I'm getting that from. So I'm putting that number in there. And so when we run the numbers through, we get an EMF of 3.7 kilovolts. Not too shabby. And then 6G and 6H have to do with simple harmonic motion. So we're not going to worry about that here. And we're done. So that's it for the 11.1 paper 2s. Just in time to watch the Super Bowl, watch the Eagles play the Chiefs. I cannot be any less excited. Thanks.